Hi everybody, welcome to the recording 7 to 10 Science Week 3. If you're watching this, currently on holidays, thank you for all the support, including coming to these seminars. I'm still trying to judge how much content makes up an hour versus am I just adding things in to make up the hour that don't really need to be there. If there's too many that don't quite make the hour, I will do an extra week at the end, or an extra couple of recorded seminars, whether or not they're live. I'll decide later on, but I will make sure that it is an average of an hour every week. So first week we did some biology. Second week, which is technically tomorrow, you're watching this in the future, will be physics, so forces, friction, Newton's laws, all that fun stuff. So I'm trying to cover as much content as I can from the 7 to 10 curriculum. Is obviously quite a lot, and I'm also trying not to kill you with the amount of stuff that we go through each week. I've uploaded probably 8 videos for these first 3 weeks, and I'll do a load more in that second week of holidays. I'll probably do an extra couple for each week in that second week of the holidays because I've only got about 10 or 12 hours to teach. So chemistry. It makes up most of the physical sciences. So it's the study of everything you can see. And it's often been sort of somewhere in between physics and biology. And there's a lot of maths, but it's also a pure science. And you're looking at the study of matter. So the things that make up all the things around us. There's a famous sort of old magic type thing called alchemy, which was taking other elements and turning them into gold. And that sort of was some of the first forays into chemistry. I mean, we obviously know we can't do that under normal conditions, special lab conditions, particle accelerators and plasma generators and things like that. Yeah, sure, we might be able to do something similar, but under normal conditions, we certainly can't. So, different branches of chemistry. Organic chemistry is the study of the molecules that are involved in, well, I say that. It was the study that, the study of the chemicals and compounds involved in living things, hence the name organic. It's now expanded to be pretty much the study of any compound that contains carbon. Inorganic chemistry is the study of the rest of the things. So all inorganic and organometallic compounds, or organic compounds that contain metals. Fairly self-explanatory. Physical chemistry is the where physics and chemistry collide. So the macroscopic and particulate phenomenon in chemical systems, so motion, energy, force, time, thermodynamics, quantum chemistry, chemical equilibrium, which if you choose to study chemistry you'll learn more about, is all where physics and chemistry sort of intertwine and become one. Don't tell a hardcore pure physicist that part of their job is chemistry. They will get very upset. Biochemistry. So a lot of people get confused, or they get biochemistry and organic chemistry mixed up. Organic chemistry is the study of anything with a carbon and hydrogen bond. that plays a role in life, in living systems. Obviously now it's expanded beyond that, but that's the most basic definition. So biochemistry, or we call it biological chemistry, it looks at the chemical processes within living systems. So if you want to study the body, you don't really like biology, then you can study biochemistry. And we've explained the process of DNA, cell division, how disease progresses and the dysfunctions of disease through biochemistry. So it's really interesting. Again, if you're a hardcore chemist, they don't like biochemists because they're a bit half. Like a little bit of biology, a little bit of chemistry. I'm not quite sure. Well, that's an electrochemist, and I like to make jokes at her expense that biochemists are just as good as electrochemists, and she gets really upset. Analytical chemistry, and that's the analysis of chemicals. I mean, I wish I had a more sort of in-depth explanation, but it just seeks to quantify all of the matter around us. Plenty of TV shows like Bones, CSI. Somebody might be too young for both of those shows to realize how old I am. But they use a lot of analytical chemistry, so spectroscopy. A lot of it made up, but still analytical chemistry. So we look at, for the most part in chemistry, we look at elements. And everything around you is made up of elements. There's 118 of them, and they make up all of the matter in the world that we live in. And we can't decompose an element into simpler substances. So I'm going to stop sharing that, and I'm going to share this amazing YouTube video. Maybe not the whole thing, but it gives you an idea of the size or lack thereof of an atom in relation to the things around it. I even skip the ad.
Atoms are ridiculous and unbelievably small. A single human hair is about as thick as 500,000 carbon atoms stacked over each other. Look at your fist. It contains trillions and trillions of atoms. If one atom in it were about as big as a marble, how big would your fist be? Well, about the size of Earth. Still hard to imagine? Let's try something different. Look at your little finger. Imagine that its tip is as big as the room you're sitting in right now. Now, fill the room with grains of rice. One rice corn represents one cell of your fingertip. Now let's zoom in on the rice corn. And now, one cell is as big as the room you're in right now. Let's fill it with rice again. This is about the size of a protein. And now, let us fill all the empty spaces between the rice corns with fine grains of sand. This is roughly how small atoms are. What is an atom made of? Let us just pretend that atoms look like this for a minute to make it easier to understand. An atom consists of 3 elementary particles: neutrons, protons.
Okay, so I won't bore you with any more of the video, but as you can see, atoms are really small. Finally, use technology again. Okay. So, atoms, or the elements, which I made up, which are acid rings. They all have symbol. They all have an atomic number. They all have an atomic weight. Most of them make sense. So Al is aluminium. H is hydrogen. F is fluorine. B is vanadium. Ne is neon. Xe is xenon, so on and so forth. But there are some that will trick you. So iron is Fe, because it's called ferrous. Its Latin name is ferrous. We have silver, it's Ag. Gold is Au. Mercury is Hg. So there are a few out there that that will trip you up a little bit. So the elements are broken up into metals and non-metals and metalloids. So metals and non-metals, and then you have these weird guys here. They display properties of both. They're this weird middle ground that there's no real agreed upon classification of what they are. But they've been in chemistry the way that it's been taught for so long now that it's just, they just deal with it, that it's there. So metals are hard, shiny, good conductors of electricity and heat. They are malleable. They can be molded. Examples are iron, which is used for building. Magnesium, which is you need a certain level of magnesium in the body. Sodium. So sodium is one part of table salt, which is something we'll look at after this. It's, if you throw it into water as sodium, it will create a big explosion. So the metals make up the majority of the periodic table. Probably, again, so I get around 3/4 of our elements are metals. So non-metals are the opposite. Poor conductors of heat and electricity, dull, and they sit on the right-hand side for the most part. Sorry, fish in my coffee. So carbon is what makes us us. If there wasn't carbon, we wouldn't be here. Silicon, which is used in computer parts, and nitrogen, which makes up almost 80% of the air we breathe. So, got metals, which are lustrous, so shiny, good conductors of heat and electricity. They have a high melting point, or they're bound together really strongly. High density, so ductile, so we can draw them into wires. So they usually are solid at room temperature. Now there's two, I think, yeah, two. Gallium and mercury. They will, if you put them in your hand, they will melt. Or mercury is already melt if you have, I think it's yeah. So if you have a thin sheet, they are opaque, sonorous, Actually, can't remember what size. I think it's the deflect sound. So they're capable of producing a deep or ringing sound. So think of big bells made of various metals. You bang them. So non-metals can be liquids, gases, or solids. They are transparent as a thin sheet, and they don't make a deep or ringing sound. So if you hit a non-metal, it's not going to give you that nice sound. So this is where it gets a bit weird. So you've got metalloids. So they display properties of both. Arsenic, tin are examples of that. So the periodic table breaks the elements up into periods. And trends are seen across, down, up, diagonally through the periodic table. We have the periodic table. It's not a perfect rectangle, but I'm just going to draw it as this. So metallic character increases this way. Goes that way. And non-metallic. Increases going that way. Just stop sharing so you can see the so the atomic radius, or the size of the atoms, increases this way. So there's this thing called electronegativity, which also corresponds to reactivity. So it goes basically like this. So that way and that way. So that means it's going up that way. Atomic radius, my apologies, actually this way. The radius also gets bigger going that way. So it's broken up into groups. So group 1, group 2, group 3, group 4, group 6, group 7, group 8, and before you say, hey, there's actually 18 groups, even all the way up until first year uni, groups 3 to 12, which are the transition metals. We don't really talk about them. So we have group 1, group 2, 3, 5, 6, 7, finally group 8. So we have periods that run across this way. And there's 7 of them. So we have groups and we have periods. On each element, you'll see a symbol. So H, you'll see 1 up here, which is the atomic number, and the atomic weight or the atomic mass unit as well. So I just spoke without restarting the recording again. So this is the periodic table. Got the non-metals over here. The majority of them are gases and solids. You then have the metalloids, which are those weird ones that can act as a metal and a non-metal. I just started speaking without sharing the screen. Okay, so got the non-metals over here, third time lucky. We then have the metalloids running through the middle here. And then over here we have the metals. Hydrogen shouldn't be over here with the metals, but it is. It breaks all the rules. So metals, these three, groups 3 to 12 here, shouldn't exist. I mean, sorry, they don't exist in your world. 7 to 10, science, you don't worry about any of them. Sorry, didn't mean to say they don't exist. So they, to your world and what your scope of learning is, you don't need to worry about them. Got there eventually. So, going to show you an amazing periodic table song. And I make no apologies. It's a rite of passage for learning about the periodic table. Let's get rid of the ad now. ASAP Science have done one. So I make no apologies for how this is.
The periodic table.
But it's amazing. It actually helps you learn what they are.
Nitrogen all through the air, oxygen through the chlorine for your creativity. I'm so right at the science, sodium for salty times.
Magnesium,
Aluminum, silicon,
phosphorus,
then sulfur, chlorine, and argon.
potassium,
And calcium, so not strong.
scandium,
Titanium, vanadium, and chromium, and manganese. This is the periodic table, no gas is stable. Halogens and alkali reacting recipes. Period, we see new outer shell. Electrons are added, moving to the right. Iron is the 26, we cobalt, nickel, points again, copper, sodium, gallium, germanium, and arsenic, and rhodium. Krypton, oxide, rubidium, strontium, the yttrium, zirconium, niobium, molybdenum, technetium,
ruthenium,
rhodium, palladium,
silver,
and cadmium, and indium,
tin cans,
antimony, then tellurium, and iodine, and xenon, and then cesium, and
Barium is 56, and this is where the table splits. Well, lanthanides have just begun. Lanthanum, cerium, and praseodymium. Neodymium's next to promethium, then 62. Samarium, europium, gadolinium, and terbium, dysprosium, holmium, erbium, helium, terbium, lutetium.
hafnium, tantalum, tungsten, then we're on to rhenium, osmium, and iridium, platinum, gold to make your rich till you grow old, mercury to tell you when it's really cold, thallium, and lead if it's for your tummy, polonium, acetate with hafnium, radar, francium will last a little time, radium, then actinize it, this is periodic table, no gas is stable, elements and help the light reactive recipe. Experience will see new outer subtlety, like color to the right, actinium, thorium, protectinium, uranium, neptunium, plutonium, mercury, curium, berkelium, californium, isonium, polonium, lithium, nobelium, lawrencium, melodium, neodymium, bohemium, mercurium, actinium, mercurium, potassium, niobium, ferrovium, moscovium, livermorium, tennessine, and organista, and then we're done.
Brilliant. Absolutely brilliant. I'm sure most of you are shaking your head. So, atomic theory is, let's say, that underpins our knowledge of what makes up atoms. So, current theory is that there is a nucleus that has protons and electrons. Protons have a positive charge, neutrons have a neutral or no charge, and electrons are going around the atom in orbits, creating a cloud. So the atom, Greek word atomos. So long time ago, they thought, hey, everything's made up of atoms. But they didn't really know what made them up. So the atoms are composed of a nucleus in the middle. Nucleus is made up of positively charged protons. Neutrons that have no charge, so they give that just give the electron its mass. The nucleus its mass, sorry. And then there's these electrons flying about in this cloud, which gives the atoms their diameter. So, protons, neutrons, electrons. That's the classic view of the atom. Lots of people get that tattooed on them. So compounds are made up of one or more atoms, and there is a chemical bond between the atoms. I mean, I'm not going to go in depth on that. There is a bond between the atoms. So salt. If we look at the periodic table, sodium on the far left, if you take sodium and you throw it into water, it will explode violently. You take chlorine, was used to produce gas, to produce chemical weapons, or is a chemical weapon in itself, really. And it's also used to regulate pH and kill algae in your swimming pool. But you put those two things together and you get lovely little crystal that makes food taste better. And sodium is actually required for our survival. We have to have a certain amount of sodium. So it is 10 to 12 as I'm recording this, just if you're wondering why I'm doing it. So element is 1. So the top row, compound, nitrogen and oxygen makes nitrogen oxide. H2O is water. NO2 is nitrogen dioxide. Should remember this one as a, what's the word, greenhouse gas. Elements and compounds are pure substances. So then we have mixtures, which can be homogeneous or uniform distribution. Think something that's dissolved in something else. And then we have heterogeneous, think oil and water, so separate phases. So water and alcohol, sugar and water, sand and water are all examples of mixtures. So heterogeneous, particles are distributed non-uniformly, so ice and soda, soil, cereal and milk, pebbles and sand, oil and water. Then you have homogeneous, which has a uniform distribution. So vodka, which is just alcohol and water, really. Steel. So heterogeneous mixtures, two phases, sand and pebbles, or oil and water. You can quite clearly see that is two phases. So homogeneous, one phase, or you can't tell there's more than one thing in there. So it appears to be well mixed. Sugar and salt dissolved in water. Mayonnaise is another one. Interestingly enough, mayonnaise doesn't have any dairy in it. Some food science, if you want to look that up. So if we have a mixture of sand and gravel, we can just use a sieve. Smaller particles go through, the large particles stay on top. Sulfur and iron. Iron fillings are magnetic. We take a magnet and we lift out all of the iron. Then we're left with sulfur and iron fillings separately. I'll explain this one. And this is the process of distillation. So distillation is used to separate two things that have dissolved into each other. So two examples, and it can be used to separate a homogeneous or heterogeneous. So we have, well, first we'll look at the classic way is distilling grain alcohol, and if you're not wondering, it's a flame. So alcohol is dissolved in water. So ethanol has a boiling point of 78 degrees Celsius, 78.37. Water has a boiling point of 100 degrees. So we have a significant difference in boiling point. So if we heat this 78 degrees Celsius, you'll get vaporization. And you guys are all probably used to my amazing artwork by now. You get vapors created. We have these cooling tubes on the outside. And as the vapor comes up, it's condensed back to liquid. And then we end up with water. And ethanol on that side. We can take a mixture of sand and water and do the same thing. So we heat this to 100 degrees Celsius. This has got, and eventually we're left with water here and sand here. I mean, we can also just take a filter and use that, separate it via filtration, but scientists don't like to do things easy. That's one way we can separate the heats. So if we take something and we look at it, is it uniform throughout? No, then it's a heterogeneous mixture. Yes. Homogeneous. Can it be separated by physical means? Yes, then it's a solution. No, then it's a pure substance. Can it be decomposed into other substances by chemical processes? No, then it's the most simple form, which is an element. Yes, then it's a compound. So solutions, where one substance dissolves into another, you have the solvent and the solute. Solvent is what you're trying to dissolve the solute into. So water is what we call the universal solvent. So a solution is a homogeneous mixture of two or more substances in an aqueous solution or a solution of water. So the solvent in this case is water. The solute is, let's say, salt or sugar. And this is possibly above, but things can dissolve into water that are the same as water on a molecular level. Oil can't dissolve into water because on a chemical level they're not the same. They don't have the same kind of bond. So charged solutes or polar can stick to the water molecules, meaning they dissolve. Non-polar, again, I'm up with those videos into the year 11, 12 one. I don't know. So body fluids and seawater are good examples of water being a solvent. So there's another kind of mixture, an alloy. And it's metals that are dissolved into other metals. So alloy wheels, we made alloy wheels not because they look fully sick, but because they're stronger and they're lighter than other materials. So the metal alloys are often stronger than pure metals. They don't corrode or rust as readily, and they improve appearance, so they're often more shiny or easier to shine. So there's oil racer alloy wheels. So air is a mixture of nitrogen, oxygen, and other gases. 20, just call it 20% oxygen, 79% nitrogen, and 1% other gases. Again, we can apply that same thinking to air. I think we've already gone through this. We could use a filter, use a magnet. So that was alright. I think it was quite a decent length of time. There's already a few of the videos for this one up. So tutorial questions: why is water considered the universal solvent? How would you separate water and sand? If you were trying to separate sugar and water, how would you do that? I will come up with a video or answer the tutorial questions for the first 4 weeks, maybe in the second week of the holidays. I just haven't had time to get onto those yet, but I'll do them all in one go. Thank you for watching, and I will see you when I get back.